So last time we finished this most famous algorithm, Dijkstra shortest path, single source graph, positive weights. So we can do this in number of edges plus number of vertices times log. So it's almost linear time. It's almost m plus n. It's amazing that in linear time you are able to calculate all the shortest paths from S to every vertex V, shortest distances and one possible shortest path. So the last topic, which is today's content, is how do you sort in linear time? Okay, so you have seen a lot of algorithms in the union of programming course and this course. So the final algorithm you will see will be a very fast algorithm, which is actually implemented in practice, and it dates more than 60, 70 years. So this is called counting sort, and then based on this there will be a faster algorithm that we hope to finish today. So here the problem is you are given an array of integers. Integers are n integers, they are small. So their value is just k or below k, between 0 and k minus 1. And you want to sort in n plus k time. So think of k as around n. So then this is linear time. You want to sort in linear time. Okay, so what you do in counting sort is, as the name suggests, you count the frequency. And then you output the array. So the array, usually in exams and quizzes and lectures, we assume that the integers are distinct. Here we will not. Here they cannot be distinct because k is very small, but n is very large, right? So clearly elements are repeating. So when these integers are repeating, so what, and the repeated integers are like, for example, date of, marks. So clearly many students get same mark, right? So so the data associated to that integer is different, but the key itself is the same in many places. So what you want when you do this on a database is that if student 1 with marks 10 appears before student 2 with marks 10 in the database, then after sorting you want to maintain this order. For unnecessary reasons, unnecessarily you don't want to swap student 1 with student 2, right? Because they have the same marks, so after you sort in the output, you keep that order. So without swapping the data of equal keys, you want to give the answer. So yeah, you will understand that better when you see the dry run of this idea. So let's take a simple example. So the array has numbers up to 5. And the indexing is usually starts from 0. So this is the case of n equal to 8 and k equal to 6, right? All numbers are from 0 to k minus 1, 5. So we make so this is the array, input array, then we make a new array called count, which should store the frequency. So basically in the ith location, frequency of I. So let's draw 0 to 5. Okay, so the thing to compute is now frequency of 0, which is, so frequency of 0 is 2, frequency of 1 is Nothing, 0, never appears. Frequency of 2 is 2, frequency of 3 is 3, frequency of 4 doesn't appear, frequency of 5 is unique. Right, so you calculate this, and from here you should already get the idea what the output, sorted output will be. Right, because what you see is that 0 appears twice, so the first two answers have to be 0, 0. Then there is no 1, so 1 doesn't appear, then you jump to 2, and that you have to repeat, so 2 and 2, right? So that basically is your algorithm, but systematically you create another array called place, which will tell you the locations where you should keep the, or where the change happens. So in the place array, what you put is so 0 comes in the first two places, then 1 will not come. So I mean, essentially we are just adding up the prefix numbers. So keep 2, then 2 plus 0 is 2, then 2 plus 0 plus 2 is 4. And then you get 7, then 7, and then 8. Okay, just this. So place is just a single scan on count. Well, count was a single scan on A. So you compute count, and then place is a single scan on count. So you compute place. Now this place array will help you give the output. Because you will see that first entry is 2, so you write 0 2 times. Then you see that the location, at location 1 you have 2, which is the same as 0. So you don't have to do anything. You don't output anything. Then you see that location 2, so which means that 2 has to appear till position 4. So you will get 0 0 2 2. Then 3 has to appear till location 7. So you will get 3 3 3, no 4, and then 5. Right? So that is how you will output. So the output becomes using the place array. Yes. Yes, in a way that is true, but I think I will write the pseudocode. Yeah, so you are saying that the pseudocode can be made shorter, so let us see. Yeah. Yes, I think that is correct. You just have to verify quickly. I mean, I want to do it in n plus k times, so yeah, so maybe you can further optimize this, but let me not try to do that immediately. So, well, it's good that you got the idea, so we just continue with the formalization. Yeah, now I remember. I want this additional property of stability. So it's for that purpose. So when I'm writing B, you will see why place is needed. So I'll do this a bit more systematically. Yeah, so the question is, why is place needed? So let us do the dry run of or how the output is created in a stable way. Um, so we will actually read the array A backwards. We'll read it from location 7. So when we see that there is a 3, so remember that 3 appears 3 times. So these are, let's say, GPA of 3 different students. So student number 2, student 5, and student 7. And whatever we output, this student 2 should be before student 5 and before student 7. Okay, so we want to maintain that order. We unnecessarily don't want to swap the data of student 5 with student 7. So there is a bag of data which is not drawn. So these students have the same GPA, but their data is big and you don't want to swap it unnecessarily. You want to keep it in the same order as input. So this is achieved by doing giving the output backwards. So you start with location 7, you see this marks or entry integer 3, and now you ask where should 3 be written? That 3, where should it go? For that, place is needed. Okay, because in place you see that 3 ends at 7. So we can be sure that this student comes here in the output. Is that clear? That's the use of place. Yeah, so actually there is a mismatch of this number. So what you have to, see when it says 7, you have to read it as 6. So this 3 should go to 6. So basically this has to, when you read off 3, location 3 here, it says 7th, it's kind of the cumulative frequency, right? So in the array, it will be 7 minus 1. It will be the index 6, so we put 3 there. Then we go to the penultimate element in A, which is 0. So where should we put 0? So you look in the array, place. Yeah, so it says 2, which means 2 minus 1. So that is the beauty of place. Okay, just by reading it, just by querying once, you know where to put this 0, and then subsequently, then you continue. So then the 3 comes. The 3, you again see that. So when you are doing this, you can update 7 to now 6. Right, because the 7 has been used, you reduce it to 6. So you change the place array. And now when you come to the next 3, you will see that it says 6, so which means 5. So you put 3 there. Okay, so this is how it is proceeding. So we have cleared this, then this, then this, and then you see 2 in array A. So 2 you read off from place, it says 4, which means index 3. And this you then reduce to 3. Okay, so hopefully this gives you the idea. So on. So is this clear? So each of these arrays is just one scan. Okay, you scan for count, scan for place, and scan for B. Say that again. You will be using multiple scans of count. No. Yeah, so that's a good question. How do you do this in one scan? So you just scan A from left to right, say, and whichever number you see, that index in count you increment. So when you reach, let's say, so when you see 2, then you should, initially count is all 0. When you see 2, then the index 2 should be done a +1. Then when you see 5, index 5 should be done a +1, and so on. Yeah, K is given. This will be, I mean, which you anyways do. Anyways, in your all your programs, in lab exam also, you do a max value setting, how big the array is, and so on. So it's the same thing. You will just give a hash define max K. Because ultimately you want the algorithm very fast, so K has to be known. If K is not known, then you will be stuck with the usual mud sort or quick sort. Okay, so yeah, I guess I will not draw this, but let's just write the main steps that we are doing above. So read, we are basically reading A backwards. And then we are putting in B. So what are we putting? First we put 3 at index so from place we read. So it's basically place. What does 3 say? So 3 says 7, so 7 minus 1, so at 6. Okay, so and then we read 0 in A, and then we put it at index, place 0 minus 1, which is 1. And so on. Okay, this is basically the guide to your pseudocode. So like this you will produce B, and the main thing here is this stability issue, that we notice that the student number 7 will be placed after student number 5, and who will be placed after student number 2. So this is a stable, so you have stability of data. We are unnecessarily not changing the order of students. So for whatever reason the students were given in the input in that order, and we will not change them unless there is a need, unless their marks are different. Okay, so that's the property we are preserving. So this question of place was a good one. It's the place array that is helping you achieve that. Any other questions here? Some people came late. Okay, so then based on this picture, we can write down the tricky pseudo code. So you have input array, size, value. So this is just a game of multiple for loops. So for j equal to 0 to n minus 1, you do initialize count. Initialize, well, you compute count now. Did I make a mistake? Count goes till k, yeah, that's a mistake. Yeah, so J, so the semantics here is J is for the key. And I we will use for index. Let's, because there will be many for loops and there will be this array notation with an array and so on. So it's nested array, so it's a bit tricky to read. So J goes up to the value, which is maximum k minus 1, initializes them to count to 0, and then you, when you want to calculate, so what is happening is A is being read from left to right, 0 to n minus 1, and the value that you see at index I, that location of count you will increment. So that short form means count AI equal to count AI plus 1. Okay, so we are incrementing, so this for loop gives you the count. And then comes the place array. So place 0 should be what? What was place 0? Yeah, so place 0 was just count 0. So do that. Once count is correctly calculated. And then the rest of place. So for j equal to 1 to k minus 1, these are the values. Place for this value j, increment it. Well, not really increment, the previous one, which is j minus 1, in that you will add count j. Okay, so this finishes both count and place. So those arrays are now correctly calculated. So whatever was, so by induction place j minus 1 is correct. Once it is correct, then you add the next value of count, that becomes next value of place. So this will give you the correct array place ultimately. And then you output. So which is so read A backwards. So in the output, which is the B array, what will you put? So this is a doubly nested or triply nested array notation. So what this is doing is you are at I in the array A, so you look at the value there, AI, then see what place array says for that, where is the place, do a -1. In that place of B, you put AI, that value. It's just like the example you saw. But it looks very tricky because there are so many, there are 3 square brackets here. And what next? Change place, yeah. So decrement it, so -1. So place AI to a -1 there. And then you read the element of a one step backwards. So this will correctly calculate the output. Is this clear? So this is the example we saw, and you can see now the pseudocode in all the details. So what is the time complexity? There are just bunch of for loops, right? Just 1, 2, 3, 4 scans. These are just 4 scans, total n plus k. So this is Sievert's counting sort implementation. So counting sort takes order n plus k time and space. And it's a stable algorithm. Since equal keys are not swapped. Okay, so 2 elements are swapped in the array A only if you are forced, which is they are in the wrong order. Like value 2 coming before value 1, then you are forced to swap. But value 2 and value 2, wherever they appear, they will stay in the same order in the output. So that's what a stable sorting algorithm is. So counting sort is linear time, is order n plus k, and it is a stable sorting algorithm. I state this here as a theorem because I will use it in the next even faster algorithm. Yeah, so any questions? So this is linear time. As long as your k is order n. Okay, so as long as your values are not too large, so suppose you have 10,000 students data, and the key that you are using is smaller than 10,000. Okay, so in that kind of a setting, you can use this. This is faster. This is much faster than the usual sorting, which is merge sort or quick sort. But of course, if you have 10,000 students and the key you are using can go up to 1 million, 1 lakh or 1 crore, then you cannot do this because this is silly. Because then you are creating an array of 1 lakh entries for just 10,000 students. Right? So you don't use this then. Then you use the merge sort kind of algorithms. So that is the remaining question. What if k is significantly bigger than n? The values are significantly bigger. Say k is n to the 10. Okay, so it's not that k is exponential, it is just that k is slightly bigger. So for 100 students, k, the values that the keys are taking are like 100 to the 10. Okay, which is easy to store. I mean, this is just 10 times log n bits. So it's not that it's hard to store the keys, but if you do counting sort, then everything goes awry. It's very slow. So what should be done here? So that is the final algorithm. It's called radix sort. So in radix sort, we will specify the input slightly differently. So you have array. Yeah, so the idea here will be we want to go inside the integer. Okay, that's a basic idea that since the keys are long, you actually look at their digits. How are they represented? So radix basically means base. It is to do with your digit representation. So in radix sort, what we will do is we'll go inside the digits, inside the integer at the level of digits. So that is what you are given. So array A of n integers. Each integer has d digits. In base B. Base is equal to B. So what does it mean? So it means that suppose one of the key is 52. Then in this representation, in the usual decimal representation, how many digits you see? 2 digits. And what is the base? 10. So just remember that if base is B, then the digits are, what are the digits? Sorry? No, not log. The digit value is from 0 to B minus 1, 0 to 9 in this case. So whatever is the base, the digits are just 0 to B minus 1. And how many digits, that can be anything. I mean, that depends on what the input keys are. So that's given by essentially D. And now if you want to write it in binary, so in binary it will be with this, right? So this should be correct. It's 4 plus 16 plus 32, I think. Yeah, so that's the binary representation. So you have more digits there. D is equal to 6. The reason is that you have taken B to be small. So when you decrease the base, then the digits blow up. So that is the representation. This is just to remind you that the base in the database, the keys are integers and they may be written in any base. Okay, not just base 10. So you use a base that helps in faster algorithm, faster sorting. So we can actually change the base. For this, use sort A. So that's the question. Yeah, so quick observations are that here, so what is K? How big are the keys? So the maximum you can write here in D digits is something like b to the d, yeah. So that will be your k if you were going to use counting sort. The key values are around b raised to d. I mean, they cannot exceed b raised to d, but they can be quite close to b raised to d. And one thing we'll assume here is that the base is smaller than n. Okay, we'll never take base, or the number of integers we'll always assume is much bigger than the base, because base will be some small integer like 2 or 10, and while n will be something very, very large. So this is a natural assumption that base is significantly smaller than n. Not even order n, you can take it to be log n. And what we want is solve this problem in dn time. Okay, so for the number of digits small, this should be linear time. That's our goal. So this is what static sort will achieve. So note that you have to compare this with counting sort and then with merge sort. So that's a lot of comparison. So for example, in counting sort you had n plus k. K here is b to the d. So counting sort will not work because that will be n plus b to the d. And b is at least 2. So this is significantly bigger than 2 raised to d. So that's exponential in d, while what you want is actually linear in d. Right? So for this, currently you don't have a solution. So idea zeros will not work. So old sorting algos, or just maybe merge sort. So this will take n log n time, which generally will be very, very, much bigger than dn. Okay, generally in this sorting problem we are looking at small keys, so d will be in particular small. So in that case, merge sort will be very slow. And similar issues with counting sort. Counting sort is n plus k, which is much, much bigger than dn. Because, well, d is much, much smaller than k by n. Okay, k is around b to the d, and b to the d is growing exponentially with d. So counting sort is very slow. Okay, so these solutions don't work. Any questions? So then we can directly give the do the sorting for an example. You will see how it works. So what we will do is use counting sort on the digits. At the digit level. Yes. Yep. No, n is growing very fast. N is like 1 million, while the keys are not that large. I mean, key, even if it is date of birth, it is just day, month, and year, right? It's just 8 numbers. So D is something very, very small. D essentially has nothing to do with N. N is your number of students or number of citizens. Yeah, counting sort is compared there. So for that, you have to compare D with B to the D by N. B to the D by N is also significantly bigger than D. So, I mean, if you are confused, whatever parameters work for merge sort and counting sort, you use that. But there is still a range where they will not work. So for that range, you have to do something else. So you can like draw a graph and check what is that range where radix sort is needed. So this, maybe this should be done a bit carefully. 1 plus k by n, no, it's okay. Yeah, so d, k is, yeah, that is the case. So I was just thinking, yeah, so b is not just 2, right? B can be anything. So if you take d to be, let's say, square root of log n, then you are looking at b to the square root of log n, which can be sufficiently bigger than n. So the ratio will be sufficiently bigger than d. So there are a lot of functions for which this is satisfied. So we will do counting sort at the digit level. That is why we developed counting sort carefully as a stable algorithm. So what we will do is the following. Your array A is given as this. These are the numbers. So the setting is there are 5 elements, 4 digits, base 10. Okay, so we have put them, instead of horizontally, we have put them vertically in a column. And what we want to do is we want to look at like a sub-column here of digits and sort using counting sort. Because the digits are very small, they are only from 0 to b minus 1, 0 to 9. So counting sort is valid, right? And number of digits in a column is n, but they are very small, so you should use counting sort. So what do you think we should start sorting with? Maximum, the most significant digit or the least significant digit? Yeah, so most of the students will say most, but that is not the right answer. What we will start with is actually the least significant digit. We'll sort from there. So here you do count sort. And so we are looking at 25103. So we push 0 to the top. And so here comes the data. So you are only looking at 0, but the associated data is there, 581. So when you when you change the location of this 0, 581 should go with it, obviously, right? Then after 0 should come 1. So 0 and 1 have been swapped. And then 2012. 2373 and 1385. Next you go to the least significant digit, just one above that. So now you have 16178. You again do count sort on that. And so 161, so you have to bring the bottom one to the top. Then you go to the third least significant digit, again sort. So 80933, you will get 03389, and with that the data also moves, right? And then we are at the end, so now we have to focus on this. So count sort on the most significant digit. Where you see 22154, so you will get 122 and 45 by count sort. Okay, which clearly is sorted. Is this clear? So this is called radix sort. All you are doing here is a single for loop, which goes from least significant digit to most significant digit, and then using that as key, it is calling count sort. Right? So it's a very simple pseudocode. Do you see where we needed count sort stability? Yeah, so here you see that stability is important, because like in the the least significant digit, when we did count sort, well, they were distinct keys, but when we did it the second time, so there you see 161, so 1 appears twice. You don't unnecessarily want to swap them. So 5810 you want above 2012. And only when there is a need, like the need comes when you have 80, then you flip it, then you exchange them. Yeah, so in the end you have to show that the numbers, 5 numbers are sorted, which is fine with 12245, because, well, if the most significant digit is 1, no matter what comes after that, the 2000 plus thing will be bigger, right? So 1 has to be in the first place and 4, 5 has to be in the last places. But you have to see why the 2 star and 2 star are correct. So that's the only thing you have to check, that these two are in the right order. So why is that sorted? Yes, so they are sorted because of because when the algorithm sees 2 and 2, it will not unnecessarily swap it. So whatever was the reason prior will continue, and the reason prior is 03, which is again which is the reason why 2012 is smaller than 2373. right? So all the logic is now tied together here. So the stability of count sort is critical. So yeah, I think this is pseudocode we don't have time to write, but let's just state the theorem. So this is by Hollerith in the pre-computer era, when there were mechanical computers or calculators. So already this was a useful thing in mechanical calculations and or mechanical machines. And then Seward make it memory efficient for digital computers. So radix sort takes how much time? It's basically D is the number of digits that many times you are counting sort, and counting sort will take n plus b, yeah, b minus 1. But somewhere we assume b to be order n, so this is dn. Okay, so you see this d cross n matrix essentially, and then you are changing the matrix. So space and time, everything is dn. So in terms of that matrix, this is extremely fast. Okay, this is like linear time in the space that it is using, because the 2001 to 2373, that is already taking d cross n space, and the algorithm time is also that. So it's extremely fast. Yeah, so there was some more comparison, but that I can put online. So if you have any questions, you can ask. So that is the last topic, and yeah, hope you and your friends enjoyed the course.